This will be another analysis of the scalene triangle that's involved with the three-dimensional golden spiral. There are two different faces, two different triangles that make up three different tetrahedra. This is actually a terminal point of the spiral. I just started here and we're gonna zoom out, start to see kind of a scorpion tail look to it. And that's as much as I can basically resolve and make on this video. Anyway, what I'm going to look into today are, we're going to analyze this triangle, but we're also going to look at like this area here and this area here and to this area here. It's the same area. It kind of goes left and right, as you can tell. And that goes on repeatedly. Let's just say that's the inner part of the curve, or the inner part of the three-dimensional spiral. Okay, so we can get back to this guy if we need to. Just put him at home or whatever. Firstly, I'm going to talk about, I don't want to deal with that yet. I want to talk about the two different plane nets of the E module or T module in Buckminster-Fuller's synergetics real quickly. Again, here's that scalene triangle that we're going to be discussing. It's this area here. This actually shows like the surface edges of the various phi-scaled E modules that build up the larger E module. And you can kind of see that you have, and I'll say this as well, just so we're on the same page, there's this I'll change that. There's a sort of a square here. It is a square, excuse me. But ideally, that would be the plane net. But this area here has to be flipped around, so to speak, so it can fold up. Because that way, this edge here will hit that edge there, and that can't fold in this orientation. I guess we can try real quickly to draw that other triangle, but see, now it's not going to be on the same plane, so to speak, but it is a plane. It is the four planes that will make that so-called T module shape. As you can see, it's actually in 3D here. I've been kind of working in a two-dimensional world for the most part. Okay, so we'll just acknowledge that that triangle exists. And it's the same on either. There's two initial alternative arrangements of the lesser sized E modules. But as you can see, there was an overall square which had essentially, there's four triangles. The one I talked about here, and then there's a larger one that's similar, and then there's this one with the yellow hypotenuse here, and then there's the scalene one. So essentially, the hypotenusae or nooses of the three right triangles are the edges of the scalene triangle, and those are three folding lines, you could say, and then the other lines, edges, would join up, such as this overall length here would line up with this overall length. Okay, we can see that the same triangles are in there at different scales of phi, and in fact, we also have a square here that's identical to the overall square, let's say, but again, this triangle here, if it was to be a true plane net, would have to be flipped around. Boy, it's hard to... Funny how that works, isn't it? I think you got it. It just doesn't want to behave. You always miss one little step. Okay, that's the triangle. It doesn't work. As you can see, it repeats throughout the whole area. Now, and there's it looks like we've got the start of another square here. You can see that those three basic triangles emanating from the same point as, as this square, or part of it, as this chunk here, it's the same to this overall chunk way up here. And that's kind of easy to show. And I find that kind of fun. Anyway, that would be like, the blue part would actually be a part of a rhombolic tricontahedron that'd be two phi scales smaller than the overall large one, which is made with this overall perimeter. Okay, so now there's another triangle here that we haven't, that isn't part of, let's say, the plane net, and that is this triangle here. Well, I better find an area where I can actually hit it. Oh boy. I'm trying to hit those little white dots. Alright. Boy, they do not want to behave. That triangle there, as you can see, it's part of this overall triangle here. Okay, and that is part of what I was calling the remainder tet. Alright, now let's move on. Here's the alternative initial arrangement. As you can see here, now the interior, let's say, tricontahedron is just one phi scale less than the overall. There. Here we only have one of the scalene triangles that is related to the initial scalene triangle, and you can see that this has two yellow edges. Well, they're not being defined right, but there's one from here. See if we can do this. It just doesn't want to show, but anyway, we got from this point to this point, and this one's phi larger from here to here. So they are intimately related, these two triangles, and they are the two triangles that are used to make all of the golden UVW tetrahedra. Whoa. Well, that's actually an interesting Clark Richter. I'm not sure why he put his wife there. I don't know. Anyway, here is that scalene triangle, but I've kind of shown the two triangles, how they work together, and it's kind of like, you can see, like, so we'll just start with this one here. I'm terrible with these little dots, but I might be able to pull it off. You can see that this area, I want to get that so it's nice and flat. I don't know if I can. It looks a little distorted to me, but it's just my eyes. Anyway, at each level where you hit this parallel to this, you are growing that triangle. And you can see that there's also the other triangle, which is the one in the remainder tet that I first mentioned, but then also the it's interesting in that the size of that triangle there and this triangle are the same. They don't look it though. That's driving me crazy. And they are though. Those two areas that are highlighted are the same. And it's making one larger scalene triangle. So there's two of the scalene triangles, which are the two red edges and the one yellow, and then the other triangle, which has got two yellow edges and one red, that make up the overall area. And there is a 2-to-1 ratio in the three tetrahedra, where the U tetrahedron is made of 4 triangles with a red, red, yellow, and the other two are made of 2 of the red, red, yellow and 2 of the yellow, yellow, red triangles. And that makes a total of 12 different triangles, 8 of them being the overall red, red, yellow, and 4 of them being the yellow, yellow, red, and that's that ratio of this in this area to just this one area here. Twice as many being used. In the UV tetrahedron, UVW, pardon me, the W is made up of just 4 of those. The W is made up of this, I'm going to say this right because I don't want to make a mistake, is made up of this triangle here and this triangle, these two here. Actually, and there's 2 of these, 2 of these, whereas the V is made of this triangle plus the next larger yellow, yellow, red triangle. that. And I don't have those readily at hand, I'm sorry, but anyway, the purpose of this video, I just wanted to show that, let me go back, I want to go back to that real quick. I wanted to show that there's this area that is being repeated on the interior of that curve of the spiral, which is from here that area, but then the next one right here that's not shaded, it actually flips the other way, which we'll look at now. Okay, so remember I said this area here, it's part of the overall red, yellow scalene triangle? Well, then the next one, because here the yellow is on the right side over here, and on the next one the yellow will be on this side. For this area the yellow's over here, and the rest are there's these two reds, this one here and this one here, are the same length, and this one's the next 5 larger red, and then there's this yellow here. And you can kind of see inside here I have the 2 triangles delineated. So in a way it's like that scalene triangle folding, but then it's alternating left and right, which I find very curious, and it kind of is very comprehensive in its utilization of the areas. And that's what I find really exciting. And I can go way in there and there's still those same triangles. I mean, that same kind of trapezoid, but it does alternate. It's made of those 2 triangles. So in reality, the 2 tetrahedron, the V and W, are the ones utilizing the yellow, red. And then, oddly, the U tetrahedron has just 4 of the red, yellow scalene triangle, and it's kind of like the glue or the fastener, let's say, in a sense. And what's also interesting about it is that in the golden, or in the Fibonacci series, you have an odd, well, actually if it counts 0 as even, you have an even, odd arrangement, and you're adding an even to an odd, and an odd to an even, and an even. You never have an even and an even, because you'd have an even and stop the cycle. But anyway, you have like the V and W are the 2 odd ones, and the U is the even one. And it actually works out in the volume relationships as well. Huh, we're missing a little area there. See a little bit of an interior in the spiral. So, in a way, let's say that the U tetrahedron is the backbone. I probably have the areas too mapped up. It's really, I'm hitting the center of the triangle here and that triangle there. That's 2 of those same red, yellow scalenes that are, they kind of are the glue, like here's one and here's one, but I'm only hitting, and I'm trying to show that area, I'm trying to show this area and this area, and they kind of fill it, and then so the U's don't have any exposure on the interior curve of the spiral, just the V and the W tetrahedron are exposing surfaces. And that's long enough. Alright, thank you.